In this video, we are going to focus on sketching and interpreting graphs of cubic functions. Cubic functions are functions of the form ax cubed plus bx squared plus cx plus d. We will use this approach to draw a graph of a cubic function. We will find the y-intercepts, the x-intercepts, stationary points, which we also call turning points. You can also call them local minimum or maximum. Then we will look at or consider the sign of A. The sign of A tells us the shape of the graph. And then finally, we will plot the graph. Let us illustrate these steps using an example. Let's say you've been given some function f at x equals to x cubed minus 6x squared plus 9x minus 4, and you are asked to sketch the graph of this function. We can follow the steps above. We can find the y-intercepts. To find the y-intercepts, we let x equals to 0, which means whenever we see x on this function, we replace it with 0. So if we do that, we will be left with minus 4. So when x is 0, y is minus 4. That is our first, that is our y-intercept. Then secondly, we can find the x-intercept. To find x-intercept, we set y equals to 0 or f at x equals to 0. When we do that, we'll be left with this polynomial. Now, to factorize this polynomial, we go back to the factor theorem. We try to find the factor that makes this polynomial equals to 0. I tried x equals to 1, which makes x minus 1 my factor. So x minus 1 is a factor. I am going to use the factorization by inspection to find the other factors of the same polynomial. To factorize this using inspection, you start by the factor that you found by trial error. Then in these open brackets, to find the first term here, we want the term that when multiplied by x will give us x cubed. That term will be x squared. X squared times x will give us x cubed. Then we focus on the last term here. So we are looking at the term that when multiplied by minus 1 will give us minus 4. So the term multiplied by minus 1 will give us minus 4. That will be 4 plus 4. So plus 4 multiplied by minus 1 will give us minus 4. Now we focus on the middle term. The middle term in these brackets, we only look at the second term of the polynomial, minus 6x squared. In this, to find this minus 6x squared, we look at this and this. We are only interested in this and that. So here we already have minus 1 and x squared. So minus 1 and x squared give us minus x squared, just 1 minus x squared. But here we have minus 6x squared. So we are left with minus 5x squared. I said we look at this and that. Now since we have minus x squared, what can we multiply with here in order to get minus 6x squared? We have minus 1x squared. Therefore here we need minus 5x squared, so that we have minus x squared minus 5x squared giving us minus 6x squared. This is the approach you use to factorize a polynomial by inspection. Now that we have found the terms, we can simplify this and solve for x, and our x equals to 1 or x equals to 4. This is the step that requires a little bit of effort. If you are not comfortable with factorizing by inspection, you can use long division or the synthetic division methods to find the factors or to find the values of x here or to solve for x. Now let us move on to step 3. Step 3 is finding the stationary points. these are the turning points of the cubic function. Like I said before, we also call them local minimum and local maximum. To find stationary points, the first thing that you do is to find the first derivative of the function. So we find the derivative of f at x, which is 3x squared minus 12x plus 9. You set this derivative equals to 0. Then you solve for x. Look, when I set this equals to 0, I divided by 3 because 3 is a factor in all of them. That's why I have this, which is different from that. Then you factorize, you get x equals to 1 or x equals to 3. You find the derivative, you set it equals to 0, you factorize, you find the values of x. Now you take each one of these values of x and substitute in the original cubic function or in the original function of f at x. We will start with x equals to 1. When I substitute x equals to 1 in f at x, I get 0. So that means when x is 1, y is 0. That will be my first turning point. 1 and 0 will be my first turning point. Then I substitute x equals to 3 in f at x. When I do that, I get minus 4. Therefore, when x is 3, y is minus 4. That is my second turning point or stationary point. Now we have found the two stationary points of the graph because we only have x equals to 1 and x equals to 3. These are the only two values of x that we have. Therefore, we have these two stationary points. Now we can consider the sign of A to predict the shape of the graph that we are going to draw. Now, when A is greater than 0, or when A is positive, like in our case, our A here is 1 and it's positive, the graph will look like this. Starts down, there we go, and then it looks up. When x is less than 0 or negative, the graph starts up, then like that. Now, our graph, our A here is greater than 0, so the shape of our graph should look something like this. Now, let us plot the graph. We can start by putting the points that we got, the y-intercept, the x-intercept, the turning point, and another turning point. Then our graph will go something like that. Before we start with the interpretation of graphs of cubic functions, let us look at the concept of concavity. Concavity tells us whether the graph of the cubic function is concave up or concave down at its stationary points by analyzing the gradient of the function. It indicates whether the gradient of the function is increasing, decreasing, or simply stationary. We will look at the second derivative to determine the concavity of the graph, which will give us its shape at its stationary points. If I have some stationary point P given by x equals to A and y equals to B, now if I find the second derivative of some function f at x and then I substitute x equals to A and then I get a positive answer, then the graph at that stationary point will be concave up. I will have a minimum here, or a local minimum. Now, if I substitute x in the same second derivative and the answer is negative or less than 0, then the graph will be concave down. Now, if I substitute the same x equals to A and I get 0, we have what we call the point of inflection. At the point of inflection, the graph changes its concavity. It's either changing from concave down to concave up or from concave up to concave down. Let us illustrate these concepts using an example. Let's say you were given stationary points A and B of some function h at x. Now, if you are asked to tell which one would be the local minimum, how would you go about doing that? Now, we first find the first derivative of the function, then find the second derivative. Then we substitute the x value of the first value of the stationary point in the second derivative. When we substitute x equals to 1, our answer is minus 6, which is less than 0. So what do we have at the stationary point? We have, our shape is concave down, we have what? A maximum. So therefore, this will be a local maximum. We can try with x equals to 3. If we substitute x equals to 3, we get a positive 6, which is greater than 0. If you substitute the value of the stationary point, the x value of the stationary point in the second derivative, and then the answer is positive, this is concave up, you have a minimum. Therefore, this will be our local minimum. Therefore, point B is the local minimum of this function. Now, to find the point of inflection of some function, we know that when we substitute x into the second derivative, it must give us 0. But we can also set the second derivative equals to 0 so that we can know which value of x which value of x will give us 0 when substituted into the second derivative. In that case, we get x equals to 2. So the point of inflection of this, we simply, so to find the point of inflection of some graph, we find the second derivative, we set it equals to 0, then we solve for x, we take that value, and then we substitute into the original function. So when you substitute into the original function, what we get is minus 2. Therefore, the point of inflection is 2 and minus 2. Here is what we have picked up from sketching the graphs of cubic functions. We have noticed that the x coordinates of the turning points of f are actually the x-intercepts of the first derivative of f. So the x-coordinates of the turning points are the x-intercepts of the first derivative of f. And also the point of inflection of f, it's actually the turning point of the first derivative of f. This information is very important in interpreting graphs of cubic functions. Let's have an example and see how this works. Let's say you've been given the function, you've been given the graph of the derivative of g at x as shown, and you are asked to find the values of x for which the actual graph of g at x is decreasing. Here we've been given the derivative of g. Now we want to know for which values of x is the original g at x decreasing. Now, the original function will be decreasing where the first derivative or the derivative is less than 0. So if the derivative is less than 0, the function is decreasing. Now, the graph, our derivative, which is the gradient of the actual graph, is decreasing between minus 2 and 1. It is below the x-axis, between minus 2 and 1. So f at or g at x is decreasing between -2 and 1. We can show that g is decreasing between -2 and 1, or we can write x is the element of -2 and 1 to show where g is decreasing. G is decreasing where its derivative is less than 0. Now the second question says, find the x coordinates of the stationary points of the original graph of g at x. We've been given the x-intercepts of the derivative of g. The x-intercepts there, it's -2 and 1. Now we know that the x-intercepts of the derivative of g are actually the x-coordinates of the turning point of the original function. Look here, the x-intercept of this are the x-coordinates of the turning point. The x-intercept, the x-coordinate of the turning point. Therefore, the x-coordinates of the stationary points of g are simply -2 and or 1. -2 or 1. Now, they say if the original graph of g is given by ax cubed plus bx squared plus cx, calculate a, b, and c. Now, the information that we've been given, it's all on the derivative of g. Now, if we derive g, we get 3ax squared plus 3bx plus c. Now, if you look at this graph, it's a quadratic function with the y-intercept at c. Now, if you look at the derivative of g, its y-intercept is at -6. That tells us that c equals to -6. If we substitute 0 in this equation to get the y-intercept, we are left with -6. Therefore, c is -6. Most of the problems that require you to find some variable a, b, or c will end up leading you to solve two simultaneous equations. You will have to use the knowledge that you know, or the knowledge that you have of the derivative or the function, to come up with at least two equations that you can solve simultaneously. Now, what we know is that the derivative of g at -2 is 0 because this is the x-intercept. So we can use that and say the derivative of g at -2 is 0. And then we can solve that in order to find our first equation. So we are going to substitute -2 in the first derivative there, and then simplify to arrive at 6a minus 2b equals to 3 as our first equation. We also know that the derivative at 1 is also 0. So the first derivative at 1 is also 0 because 1 is also the x-intercept. So y is always 0 when we find the x-intercept. We can substitute and simplify to get 3a plus 2b equals to 6 as our second equation. Now we have got two equations, 1 and 2. We have 6a, 3a, we have minus 2b, we have 2b. So if I use elimination, I can actually find the values of a and b. In this case, I'm going to add equation 1 and equation 2 so that 2b and minus 2b can cancel out. And then I'll be left with 9a equals to 9, giving me a equals to 1. So far I have found c equals to -3, a equals to 1. Then I can take this a equals to 1 and substitute in this equation or that equation. I'm simply going to substitute it in equation 2 to get my b. So whenever I see a here, I put 1, then my b will be equals to 3/2. So the values that I've been required to find: a equals to 1, b is 3/2, c is -6. Here we are given information for two cubic functions, g and h, and we are asked to draw the sketch graphs of g and h by simply using the information that we're given without first finding the equations of the graphs. Please feel free to pause the video and try these examples yourself. Now let us start with A, the graph of G. We are told in this first statement that G at minus 6 is equal to G at minus 1.5 is equal to G at 2. They are all equals to 0. Now when G is minus 6, you get 0. G is minus 1.5, you get 0. G equals to 2, you get 0. This tells me that minus 6, minus 1.5, and 2 are the x-intercepts of the graph. These are the x-intercepts because when x is minus 6, y is 0. When x is minus 1.5, y is 0. When x is 2, y is still 0. So these are the x-intercepts of the graph. We can show this on the graph that minus 6, minus 1.5, and 2 are the x-intercepts of the graph. The second statement says the first derivative at minus 4 equals to the first derivative at 1, and they are all equals to 0. So if I substitute minus 4 in the first derivative, I get 0. If I substitute 1 in the first derivative, I get 0. That tells me that minus 4 and 1 are the x-coordinates of the turning points of G. Remember, when you substitute the x-coordinate of a turning point of G in its derivative, you get 0. So minus 4 and 1 will be the turning points, or will be the x-coordinates of the turning points of G. Now G could come this way or that way. It could come, yes, it could be this way, that way, this way, or it could be this way, that way, this way. Now let us read the third statement. The third statement says the first derivative of G is positive or greater than 0 when x is less than negative 4 or when x is greater than 1. What does the negative derivative, or what does the positive derivative of a function mean? Remember, the derivative of G is the gradient of G. The gradient of G is given by its first derivative. So if its gradient is positive, that simply tells me that the function is increasing in this region. Now the function is increasing, which means the function goes like this when x is less than 4 in this portion. So it's going up like that. And it's also increasing when x is greater than 1. So once I go past this, the graph increases like that. And the graph is decreasing. Its first derivative is less than 0 in the region minus 4 is less than x is less than 1. So in this region, the graph is decreasing. Now you can tell that the graph will go something like that, have a turning point there, touch the x-intercept, and then have another turning point and go up like that. So this is the graph of G that we draw simply from the information that we're given without having to find the equation first and follow the process of drawing the graph. Let's now go to h at x. In h at x, we are given that h at minus 3 is 0. Now that is the x-intercept. So when x is minus 3, y is 0. So our x-intercept, the first x-intercept is minus 3. We are also told that HH0 equals to 4. So when x is 0, y equals to 4. This is our y-intercept. Now, if you look at h at minus 1, h at minus 1 is 3, and the first derivative at minus 1 is 0. Now, this tells you that at minus 1 we have a turning point. The turning point which happens at when y is 3. So we have a turning point there because the first derivative at minus 1 is 0. But again, at that same minus 1, we have an inflection point. Remember an inflection point? When you substitute minus 1, then you get a 0, you know that you have an inflection point. So at minus 1 is a turning point because of this information. Minus 1 is an inflection point. And when we substitute minus 1 into the original function, we get that the y value of the inflection point is 3. Now we are told that, let's see, we are also told that the graph of h, it's increasing all the way except when x is minus 1. Let's have a look at this. Minus 3 is the x-intercept. 0 and 4. Okay, minus 3 is the x-intercept. We have it here. 0 and 4 is the y-intercept. When x is 0, y is 4. Obviously, when x is 0, we set x equals to 0, we get 4. That would be the y-intercept. The y-intercept is here. And we have a turning point here because of this information. When we substitute that in here, we get 3. So that's the turning point. But also the same point is the inflection point. So how will the graph look like? Obviously, because the function is increasing all the way, so the function will go that way, get there, and then continue on its way to the top. Let's try yet another example, which is similar to the one we just did, where we have to draw a sketch graph with just the information that we've been given. In this case, we've been given a cubic function g, and we are required to draw the sketch graph of g indicating all relevant points, given these 3 statements. The first statement says g at 3 equals to g prime at 3 equals to 0. Now, when x is 3, g is 0. This tells me that at x equals to 3, I have an x-intercept. My x-intercept point is 3 and 0. So when x is 3, y is 0. And this part of the first statement says g prime at 3 is 0. Now this tells me that x equals to 3 is the x-coordinate of the turning point of g, because g prime at 3 gives me 0. So this is the x-intercept of g prime. The second statement says when x is 0, y is 27. This tells me that 0 and 27 is the y-intercept of g. I can indicate this information on a graph to show that I have the y-intercept at 0 and 27. I have the x-intercept at 3 and 0, which happens to be the turning point of the graph. The third statement tells me of the shape of the graph. I've been given that the second derivative is positive when x is less than 0. Remember, this is the statement. This statement tells us of the concavity of the graph, or the shape of the graph, whether the graph is concave up or concave down. We know that when the second derivative is positive or greater than 0, then the graph is concave up. So when x is less than 3, this region, the graph is concave up. And when x is greater than 3 in this region, the graph is concave down. We can join this to show how the graph looks like. It is concave up when x is less than 3, and it is concave down when x is greater than 3. So this is the graph of G that we were required to draw. Here we are given yet another function in which we are required to find the values of B, C, and D. We are told that -5 and 0 is the x-intercept, and 0 and 20 the y-intercepts. P and R are the turning points. We are required to find B to show that B is 1, C is 16, and D is 20. Now there is one thing that you need to note about cubic functions. If you have a situation where a point is a turning point and it's also the x-intercept, like P. If you look at P, P is the turning point and it is also the x-intercept because it touches the x-axis there. When you have this situation, it means that you are going to have a repeated factor in your equation of g at x. Now we can show that by doing this. I have x minus x plus 5 for this factor, and I will have x minus some number that I don't know at P, but this will be repeated because P is the turning point and it is also the x-intercept. So this will be repeated. Now I don't need to worry about A because it's been given here, it's 1. So I can simply just ignore it because it's 1 over there. Now I was told that G at 0 is 20 from the statement. G at 0 is 20. I can substitute in this information or in this equation in order for me to find the value of x1. So I'll have 20, A is 1, x0, x0. I'll be left with this, which can be simplified to look like that, giving x1 squared equals to 4. Therefore, x will be plus minus 2, but in this case, x cannot be minus 2. Remember, this is the positive x-axis. Therefore, I will take only x equals to 2. So at P, I have x equals to 2 and y equals to 0. Now I can expand this equation because I already have the information that I need. Now I have x plus 5, x minus 2 squared, which I can fully simplify to x to the power 3 plus x squared minus 16 plus 20. Now from this equation, I can be able to get the values of B, C, and D. My B is 1, my C is minus 16, and my D is 20 if you look at that equation. So therefore B is 1, C is 16, and D is 20, which is exactly what they were looking for. Now the second part of the question, it wants us to find the coordinates of P and the coordinates of R. These are the turning points of the graph of G. Remember, to find the turning points or stationary points of a cubic function, the first thing that you do is to find the first derivative of the function, set the first derivative equals to 0, and then solve for x. So you're going to get the values of x that you solve from the first derivative. Then you substitute these values in the original graph of g at x here. When I substitute g at minus 8 over 3, I come at 1372 over 27. And then when I substitute g at 2, I get 0. So my stationary points at x equals to 2, this is P, I get 0. So at P I have 2 and 0. and then at r I have minus 8 over 13 and 1372 over 27.